Okay, looks like it's recording, so let's get started. Okay, so we'll begin with that extra problem that I put on the WhatsApp group, and then we'll go through those questions 2 and 3 of the assignment. Okay, so this problem is quite similar to what you'll be doing in the next part of the module. Okay, so in this first part, we were dealing with gases and engines with ideal gases and so on. In the next part of the module, you'll be dealing with other systems. So just as an introduction, this one, so we were given the free energy for a spin system. Okay, so you've got a collection of n spins in a magnetic field. They can be either spin up or spin down. And depending on the temperature of the environment, you have various different configurations of the system. Yeah, but for this problem, you don't have to worry too much about that. We're just doing calculations here. In the next part of the module, you'll be more focused on the types of systems and interactions in the system and so on. So a more detailed view. Okay, anyway, the free energy is minus n kBt, the natural log of 2 hyperbolic cosine of epsilon over kBt. Okay, so that epsilon is just a positive constant. Okay, so this is the free energy. What we want to do first is calculate the entropy. So we know how to do that. The entropy S is given by minus dF by dt. Okay, if you ever forget that, you just start off with F is equal to U minus TS, find the differential, and then you'll find this. Okay, so whenever you forget something, start off with the definition of the free energy, take the differential, and then you can use those partial derivatives to find this. Okay, so minus dF by dt, so that's going to be d by dt of n kBt, the natural log of 2 hyperbolic cosine of epsilon over kBt. And one more bracket. Okay, so we need to use the product rule because we've got 2 functions of t here. So the first one is going to be nkb, the natural log of 2 hyperbolic cosine epsilon over kBt. Okay, and then we have a plus, and then now we do the other part. So that's going to be n kBt times, now the derivative of the natural log is going to be 1 over the stuff inside. So it's going to be divided by 2 hyperbolic cosine epsilon over kBt. And then we differentiate by this, so we're going to get 2 hyperbolic sine epsilon over kBt. And one more derivative, minus epsilon over kBt squared. Okay, so we can simplify this now. So we're going to get nkb natural log 2 hyperbolic cosine epsilon over kBt. And then for the next one, hyperbolic sine over hyperbolic cosine, that's going to be hyperbolic tan. We've got a minus from that last bit that we did. So it's going to be minus n epsilon. We've got a t at the bottom. And then it's going to be hyperbolic tan of epsilon over kBt. Okay, now you can leave it like this. That's perfectly fine. However, just a bit of advice when it comes to these types of calculations, you should take note of where the units are. So hyperbolic tan, that has no units, right? So the input has no units, the output has no units. Same thing with the natural log. If you're inputting something, there's no units involved, and the output also has no units, which means this nkb, that is where the units are for this expression. Okay, so kb has the units of entropy. We saw that a while back with S is equal to kb log omega. Okay, all of the units are in this kb term. So, okay, like I said, you can leave it like this. or we can rewrite this in a way that makes a bit more sense with regards to this units. So I'm going to write this as NKB, natural log of 2 hyperbolic cosine epsilon over KBT minus, and now you see at the top we've got, for this next term, at the top we've got epsilon. Sorry, at the top we've got epsilon here, and at the bottom we've got T. Now we know that KBT is an energy term, right? KBT has units of energy. Epsilon also has units of energy. But we see that in the denominator, we're missing a factor of KB. Okay, so it should be KBT. So we're going to multiply the top by KB, and we're going to multiply the bottom by KB. Okay, so that doesn't do anything, but you'll see why now. So NKB epsilon over KBT. And then we have tan hyperbolic epsilon over KBT. So again, we always have this KBT term together. Now, notice that we've got NKB in the front here, and we've got NKB over there. We can factor that out. So this is S is equal to NKB, natural log of 2 hyperbolic cosine epsilon over KBT minus epsilon over KBT, tan hyperbolic of epsilon over KBT. Now you see how much, I don't know, quote unquote, nicer this looks in terms of units. So this epsilon and the KBT, those are always together. You've got an energy term at the bottom, energy term at the bottom, energy term at the top, energy term at the bottom. So that has no units. Same thing with this other term here. We've got epsilon, which is an energy term at the top, energy term at the bottom. So altogether, no units. So we're left with this NKB at the front, which has units of entropy. Again, it's N times KB. So what you can do now is, since entropy is an extensive variable, we can divide both sides by NKB, and we get S, let's call it S bar, is equal to S over NKB, and that's equal to the natural log of 2 cosh epsilon over KBT minus epsilon over KBT tan hyperbolic of epsilon over KBT. So you see now this quantity on the right-hand side, it has no units, which is nice, good to work with. Okay, and it's also independent of system size, which is also good. So here we have a quantity with no units. So it's unitless, sometimes called dimensionless. And is independent of system size because we divided by the system size, which was n. So if you have a spin system with 2 particles or 2 million particles, this term on the right here doesn't depend on how many you have and is independent of system size. In this case, n. Okay, so this previous answer that I wrote here, that's perfectly fine. However, you should get into the habit of writing things like this, okay, where it's nice and unitless and independent of system size, if possible. Okay. So again, it's not compulsory to write it like this, but you should get into the habit of doing it. Okay, so this is a unitless or dimensionless equation. Okay, any questions on that? Okay, let's have a look at the next question. That was finding the internal energy. Okay, so we know F, we know S, we want to find U. So remember F is equal to U minus TS. Okay, and we know most of these. We're trying to find U. So F was minus NKBT natural log to hyperbolic cosine epsilon over KBT. And that was given to us. This is equal to U minus T times S, but we've already found S before, so we can just substitute. So that's minus NKBT, natural log of 2, again, hyperbolic cosine epsilon over KBT. And then we had that extra term, but now with the plus, N epsilon over tan hyperbolic epsilon over KBT. Okay, so some things cancel here. This NKBT natural log, that term over there, we can get rid of that on both sides. And we can take the U to the other side. So we get U is equal to minus N epsilon tan hyperbolic epsilon over KBT. Okay, and again, we see this, this thing about the units. Here, epsilon, that had units of energy. N doesn't have any units, that's just the number of particles. Tan hyperbolic, that has no units, it's just one of those functions. So all of the units are involved in this epsilon term. So if we wanted to find the unitless internal energy, we could divide through by epsilon, and then we have it in terms of N times tan hyperbolic. That is extensive, right? You double your system, you double your internal energy. So we can also divide through by N, and that will make it independent of system size. So again, we can define this thing U bar, or you can call it whatever you like. I'm just calling it U bar for now, is U over N epsilon, and that's minus tan hyperbolic epsilon over KBT. And again, if we look at this right-hand side here, this is unitless, which is good. Okay, so you can use SI units, other units, centimeters, meters, whatever. Whichever units you use, they're all going to cancel out for this right-hand side to be unitless. And it's size independent because we've divided through by N. Okay, so it's just a better thing to work with. Okay, something that is unitless and size independent. Just for example, if you calculate this over here, and you want to work out what is the internal energy for a system of 10 particles or 1,000 particles, you don't need to recalculate anything. You just multiply by the size of the system, and then that will give you the value you're looking for. Okay, again, because it's extensive, if you have two subsystems added together, you just add the results. Okay. Any questions on this one? Okay, not so bad. Let's have a look at the third one, and that was finding the heat capacity. Okay, so we know that the heat capacity is going to be du dt. That's just how we define it. We've just found U, so we can calculate C now. So C is d by dt of what we just had, minus n epsilon tan hyperbolic of epsilon over kBt. Okay, pretty straightforward to differentiate this. We're going to get minus n epsilon. The derivative of tan hyperbolic is sec hyperbolic squared, similar to those trig functions. So this is going to be sec hyperbolic squared of the inside bit. okay, times the derivative of the inside bit. So that's minus epsilon over kbt squared. Okay, and of course, you can leave it like this. That's perfectly fine. However, let's stick with our theme of unitless and size independent and work on it a little bit more. So C is going to be equal to, the minus and the minus are going to cancel. Epsilon and epsilon are going to multiply. So it's going to be n epsilon over kbt squared. And then we have sec hyperbolic squared epsilon over kbt. Okay, so almost there. Now the clue that we need to look for when trying to make this nice and unitless and size independent is this bottom bit here, kbt squared. So, yeah?
Is it supposed to be epsilon squared?
Oh, yeah, sorry, epsilon squared, there we go. I think I said it was squared, but I didn't write it down.
Okay, no problem.
Okay, so n epsilon squared over kbt squared. So again, that's fine the way it is, but we want to try to find a unitless form of this. It's just nicer to work with. So look in the bottom, we've got kbt squared. Remember what I said earlier about the kbt? Whenever you got formulae involving that, they're always next to each other. It's always kbt. So here we have 1 kb, but we've got t squared. So there's a kb missing. So we can write this as the same thing, but multiply the top and the bottom by kb. So we're going to have n kb epsilon squared over kbt, all of that squared. Sec hyperbolic squared epsilon over kbt. Now the next thing to notice is that epsilon is always being divided by kbt. Okay, because we've got this energy term at the top, energy term at the bottom, they cancel to give something that's unitless. Okay, it's like having a length divided by a length that has no units at the end. So over here for this beginning bit, the prefactor, we've got epsilon squared at the top, kbt, all of that squared at the bottom. Let's put that together. So C is equal to n kb. We've got epsilon over kbt squared, sec hyperbolic squared, epsilon over kbt. So you see how we've got this common factor of epsilon over kbt, which is nice and unitless. Okay, so we just have to deal with this prefactor of nkb. Now, we already said everything to the right of that is unitless. N is unitless, so Kb has units of heat capacity. And N, that is just the amount of system you're dealing with. And again, remember, heat capacity is extensive. So what we can do is divide through by NKB, and we will get something that is both unitless and independent of system size. So C, let's call it C bar, sticking with this bar theme. I think if you look on Wikipedia, you might see things like T star for something that is unitless. Unitless temperature, for example. But you can write down whatever you like, as long as you make it clear what it is. So this is going to be C over NKB. Okay, the numerator has units of heat capacity. The denominator has units of heat capacity. They cancel nicely. And we're also dividing by the system size. So C bar is both unitless and independent of system size, which is great. And this is equal to epsilon over kBT, all of that squared, sec hyperbolic squared, epsilon over kBT. And that is our unitless heat capacity. Okay, and this also helps check to see if you've done the right calculations. So in the end, your units should match. So if you're calculating heat capacity given a free energy and your answer has something like epsilon cubed, okay, well then something's gone wrong there. And then you can go back and check. Okay, so just a quick check of your units can help you check if you've made a mistake or not. Okay, and again, it's not compulsory to write it like this, but it does help just to clarify what you're working with. Okay, any questions on that?
So do you mind giving us one more to try for today?
Yeah, sure. I can give you another one.
Just send it on.
Yeah, I'll post it on the WhatsApp group and then you can have a look there.
Okay, thank you, sir.
Sure. Okay, let's have a look at those two assignment problems. Okay, so I think the first one, let's just get that here. So not assignment, the hand-in problem. It was questions 2 and 3. There we go. Okay, so question 2. The most probable speed, Vp, is the speed at which the probability density function is a maximum. Okay, so that's what we covered in that one lecture. So what we want to do is find the velocity such that f is a maximum. So this needs to be a maximum. Sorry, oh, this pen's not working. Just give me a second. Okay, pen's working again. Okay, so we want to find the maximum of this function. Okay, in other words, the velocity v that makes this a maximum. So we know what this function looks like. We plotted it last time. It was something like this. And this point here, that is going to be Vp, because that's where we have a maximum here. Okay, so remember back to your Math 130 days. If you want to find the maximum of a function, you differentiate, set it equal to 0, and then solve. Okay, so that's what we're going to do here. We have f of v is given by m over 2 pi kbt to the 3/2, and times the exponential of minus mv squared over 2 kbt. Okay, so let's find the derivative. So f prime is going to be, the constant in front doesn't do anything, so we'll just leave it there. M over 2 pi kbt to the 3/2. And now we need to differentiate. Okay, so differentiating the exponential, we're going to get, sorry, there's, sorry, there's a v squared missing here, v squared. Sorry about that. If you looked in the notes, there was the v squared. Let me go back here.
So will we get penalized because I have already submitted?
No, but you should have known from when we did the lecture. So lecture 6, here we go, lecture 6, I put the v squared. But that's fine. I won't worry about that much. I won't worry about that. But let's just go through it again.
Okay.
Okay, so we're differentiating. Let's differentiate the first part. So that's going to be exponential minus mv squared over 2 kbt times minus mv over 2 kbt. Okay, so that's that derivative times v squared plus, and then we differentiate the next one. So that's going to be exponential minus mv squared over 2 kbt times 2v. Okay, and then we want this to be equal to 0. So the exponential terms, we can get rid of those, that and that. So we're left with minus mv cubed over 2 kbt plus 2v is equal to 0. We can get rid of one of the v's on both of those terms. So we have minus mv squared over 2 kbt sorry, the 2 gets cancelled from that 2. So just with this term here, when we're differentiating this, we have the 2 coming down. That cancels with this 2 at the bottom. So that goes away there. Okay, plus 2 is equal to 0. So we're going to have mv squared over kbt is equal to 2. V squared is equal to 2 kbt over m. And then we can take the roots. So we have Vp, the most probable velocity, is the square root of 2 kbt over m. And we only take the positive one because remember, we only deal with the magnitude of the velocities. So it's plus. Yeah. Okay, so I won't penalize you. I did make the mistake there, but you should have noticed that. Okay. So there should be that v squared.
Without that v squared, without that v squared, when you differentiate and all, you'll get v is equal to 0.
Yeah, without the v squared, it makes no sense. So yeah. If you take the v squared away, it doesn't mean anything.
But then that will also affect the next question too.
Yeah.
Because it have v cubed.
Yeah, but v cubed. Yeah, I mean you could still do it if you looked up the correct function.
Yeah. No, but I'm just saying I never include that v squared from the first one, so it will also affect my question 3.
If you didn't include the v squared, it means you weren't listening in the lectures, right? Okay, so yeah, don't worry about that. I'll have a look at the working you did, but please remember that there is the v squared. So in the test, it is given with the v squared, but just just for the sake of remembering, there is this v squared term. Okay, so in the previous lectures here, when we went through everything, I did emphasize this v squared. Okay, remember we converted to the spherical coordinates, and then we got that v squared term. Okay, so just remember that it is there. Okay, let's have a look at question 3. I won't do this one as is here. I'll show you the more general way of handling it. And then that trick with the n factorial. Okay, so it helps out a bit with these types of questions. Okay, so we're trying to calculate, v, so that is the integral from 0 to infinity. Let's go, it was 2 pi m kb t. Oh, sorry, m over 2 pi kbt. To the 3 over 2, and then we have the v with the other v squared, so that's v cubed. Okay, and then times e to the minus m over 2 kbt dv squared. Okay, so that's what you would have for the usual v, right? But I'm going to generalize this to vn. So if you have an nth power, so this would now become v to the 2, was it 2 plus n? Okay, so I'll show you why now. So if I do it for a general power like that, we're going to get something like this. Okay, so this is going to become the integral from 0 to infinity. We can take the constant out. So it's going to be m over 2 pi kbt to the 3 over 2, integral from 0 to infinity, v to the 2 plus n, e to the minus mv squared over 2 kbt dv. Okay, so how do we deal with something like this? As you said on the group, this is a Gaussian, e to the minus, something like e to the minus x squared. You could do it like that, but it's very difficult, okay, because you have to do, you know, the derivatives and integrals of Gaussians. That involves higher level maths. We don't want to worry about that. So instead, we're going to do a change of variables. So we're going to say, let x be equal to, let x be equal to mv squared over 2 kbt. So whatever's in that exponent, we want to simplify it so we don't have to deal with the whole m over 2 kbt. Okay, so let's find dx for the u substitution. So dx is going to be mv over kbt dv. Okay, good. Now notice how we need to get v to the 2 plus n. Okay, the 2 came from the v squared from the formula. The n came from the fact that we're doing the expectation of v to the n. Okay, so let's multiply both sides by x. So we're going to have something like x dx is equal to m squared v cubed. Oh, sorry. Sorry, not that. We can just leave it like this. Okay, so dv. So we're going to take one of the v's out. Okay, so we got v to the 2 plus n. We're going to take one of them out, and that's going to match with this v dv over here. Okay, so kbt over m dx is equal to v dv, and we're going to substitute that in. Okay, so this is going to be the integral from 0 to infinity. Sorry, I forgot the prefactor. So we're going to have m over 2 pi kbt to the 3 over 2, integral from 0 to infinity. V to the 2 plus n, we took one of the v's out, so it's v to the 1 plus n. Okay. E to the minus mv squared over 2 kbt. And the one of those v's we're going to take to the other side, v dv. Okay, so this term right at the end here, v dv, that's going to be part of the u substitution. This mv squared over 2 kbt, remember that was our x. Okay, so we're going to have m over 2 pi kbt to the 3 over 2, integral from 0 to infinity, v to the 1 over n. What's that going to be? Well, we can use this to solve for v. So we're going to have 2 kbt over m times x is equal to v squared. If we root both sides, we're going to get 2 kbt over m to the 1/2. X to the 1/2 is equal to v. v to the 1 plus n is going to be this left-hand side to the power 1 plus n. Okay, so we're going to end up with 2kbt over m to the 1/2 to the power of n plus 1. So we can just put an n plus 1 here. Okay, times v to the 1 plus n is going to be this, this term here with the x to the n plus 1 over 2. And then we're going to have e to the minus x. And v dv, that's going to be kbt over m dx. Okay, so now everything that is not an x term, we're going to take out. So this is going to be m over 2 pi kbt to the 3 over 2, 2 kbt over m to the n plus 1 over 2, and kbt over m. And then lastly, we have the integral from 0 to infinity, x to the n plus 1 over 2, e to the minus x dx. And now this you should have done in Math 140, but we'll go over it again. So you're going to do your integration by parts on this, okay? And then after a couple integration by parts, you'll see a pattern where this is actually equal to n plus 1 over 2 factorial. Okay, so this integral is another way of writing the factorial. In fact, if you have integral from 0 to infinity, x to the k, e to the minus x dx, this is k factorial. Okay, so that's something that you should remember. Okay, so you just use that, and then you don't have to do the integral, because whatever your exponent of x is, that's going to be your factorial. You just multiply that on, and then that gives you your final answer. Okay, so just remember this little formula here. So this will help a lot. Okay, so the first thing you need to do is look at the exponent of your exponential. We want that to be e to the minus x. Okay, because if we look at our formula, we need e to the minus x. Then you do all of your u substitution to simplify everything, substitute your variables, all of that, and then you'll get something that looks like this. Okay, and then you just look at the exponents of x, and then just use this formula here. Okay, so that's going to give us k factorial, where the exponents is k. Okay, and that's a general thing for any power of v. Okay, have you seen this before? This integral form of factorial?
I think so. In the last semester book, the introduction to quantum mechanics, they had the integrals at the back involving this.
Okay, yeah, you'll find it there as well.
So is it okay in the test if we use the formula, the integral, instead of doing the whole?
Oh yeah, of course. Yeah, so if it comes up in the test that you need to do this integral, then all the formulae will be given to you.
Okay.
Yeah, so in like Math 140, you would have to show all your working. But at this stage, we just say, you know the formula, just use it, you know, rather than doing all the maths. So it will be given to you. Okay, any other questions?
Maybe we can, if you have time, maybe you can also provide us with another problem on like this part where we derive and then we use the integral, like how question 2 and 3 is.
Yeah, sure. I can write something up and then I'll post it on the group. So another little practice test kind of thing.
Thank you, sir.
Yeah, sure. Okay. And then I think everyone should have submitted their problem 6 thing. So I'll mark that and then upload the results. And then remember this Friday that assignment is due as well. Okay, so then I'll be taking that as an extra hand-in problem, you know, to give you a little mark boost. Okay, and then just on that the next part of the semester, it should be the same sort of assessment kind of thing. So you'll have your hand-in problems to do, your tutorial problems to do, and then 2 tests. Okay, and then depending on how things go with those 2 tests, then we will have the supplementary tests right at the end of the semester. Okay, but then that will be everything on my part for this beginning part of the semester and the end part. Okay, so that will be the supplementary tests.
How is the next part? Is it a bit more challenging or more calculations?
No, not really. It's pretty much, you know, what we were doing here. This bit, calculating heat capacity, internal energy, all of that. It's doing all of this. However, for these examples, where is it? For these examples, I gave you the free energy. So over here, we always started with me giving you the free energy. For the next part of the module, you'll be finding the free energy yourself.
Okay.
Yeah, so it's but then everything else is the same. So the entropy, internal energy, all of that stuff, that's the same. Okay, if you want to look up some of the stuff before you start, look up thermodynamics, partition function. Okay, so that's what you'll be calculating as your step 0. So you're given a system, you calculate this thing called the partition function, and then using the partition function, you get your free energy or your Gibbs free energy or something like that. And then that's step 0. And then step 1, again, find the entropy, find the internal energy, and so on. Okay. And then you'll see on Wikipedia, it's usually given by Z. So you calculate that function Z, and then the free energy is minus KB natural log of Z. And then from that, this is step 0. And then from your step 0, then you go into your step 1, 2, 3, like we did with this problem. Okay, so it's just a little bit more to do. Okay, I think that's enough for now. I'll post the extra problems on these type of problems here, calculating the entropy and that. I'll post, I don't know, let's say three more problems for you to try. And then more on that Boltzmann stuff. You can try that as well. Okay, but that'll be a bit later today. If you do have any questions later on, please just ask on the WhatsApp group as well. Okay, I can help you out there. Okay, bye everyone.